used the uniqueness of solution to find the potential for a charge kept in front of a metallic surface or a metal or a surface which was grounded or which had V equal to 0. And we found that the potential can be obtained by putting a minus q charge for a charge q in front of the surface, which is at a distance z at the same distance from the surface. We also calculated the surface charge sigma, which came out to be q over 2 pi z naught over s square plus z naught square raised to 3 by 2. Now, what about the force on this charge if it is brought in front of a metal surface? Because it will obviously be attracted by these negative charges, so there is a minus sign here, negative charges that have been induced on the surface. Or can we calculate the force directly from this minus q? It so happens that the force on charge q can be calculated as the force between these two charges, the charge itself and its image charge, and therefore force on this is given as 1 over 4 pi epsilon 0 q square over 4 z0 square, and it is attractive. So let us put z unit vector with a minus sign here. Notice that this goes as 1 over 4 z naught square. I leave this as an exercise for you to calculate force on q by the induced charge density sigma s z naught and show that this is equal to this. What about the electrostatic potential? Electrostatic potential of charge q. Is it that we have this image charge q and the image charge minus q at a distance z0, z0? Can I write the potential V as 1 over 4 pi epsilon 0 q square over 2z0? Because this is the potential energy between two charges, and the answer is no. There is a very simple reason for that. The reason for that is that, remember, when we calculate the potential due to a given charge distribution, we can write this as integration rho r prime over r minus r prime dv prime 1 over 4 pi epsilon 0, and it is the work done in bringing a charge from infinity to that point, provided the charge density remains fixed, it does not change. However, notice in this case the image charge problem, as charge comes in or goes out, the charge density sigma depends on z0, and therefore I cannot use this formula directly. Use of this formula directly gives me this answer, with rho being the delta function. In this case, I explicitly must calculate the work done. So let us calculate the work done in moving. Work done in moving charge q from z0 to infinity, and that work done W is going to be the potential energy difference of the charge particle at infinity minus V at z0. So let us calculate this. The force on the charge is minus z 1 over 4 pi epsilon 0 q over 4z square if it is at a distance z. The force applied by us is going to be 1 over 4 pi epsilon 0 in the z direction, q over 4 z square. So work done by us is going to be 1 over 4 pi epsilon 0, I'm sorry, this is q square integration 1 over 4z square dz moving from z0 to infinity. And that gives me 1 over 4 pi epsilon 0 q square over 4 z naught, and this is equal to V potential at infinity minus potential at z0. Taking at infinity the potential to be 0, I get V z0 equals minus q square over 4 pi epsilon 0 1 over 4 z naught. So it's not 1 over 2 z naught, but 1 over 4 z naught. These are known as, this is known as the image potential. So V z at a distance z in front of a grounded surface or in front of a metal which is at 0 potential, the potential energy of a charge q is given as minus 1 over 4 pi epsilon 0 q square over 4 z naught, and this is known as the image potential. I again emphasize this is not equal to like the electrostatic potential that we calculate between two charges at a distance 2 z naught, because in this case as you move the charge, the test charge, which is q in this case, the charge distribution itself changes. So we have calculated the potential and the force on the charge due to the image charge. We have already calculated the surface charge density. What I like you to do is calculate the potential due to sigma s because of the charge at z0 and see what the result is. A related problem that can be solved using image method is if I take a sphere, say metal sphere, and ground it, that means the potential on this is 0, and take a charge q in front of this at a distance, let's say d, from the center of this sphere. It so happens that in this case also I can find another charge outside the region of interest. That means my region of interest here is this outside volume. I can find charge inside this metal so that the boundary condition is satisfied. What is the boundary condition here? V at infinity is 0. And if I take this as the center or the origin, then V at r equal to r, if r is the radius of the sphere, is also 0. If I can find another charge that satisfies, that combined with this potential of q satisfies both the boundary conditions, then I have found my solution, because that's a unique answer. So let us try and see if I put a charge inside along the same line as the center line which joins the center of the sphere and the charge q, a charge q prime, and see if I can satisfy both the boundary conditions. So let us write the potential V at r vector. Now I am going to take this direction to be the z direction. You imagine a bit that I have taken this direction to be the z direction. If you cannot, then I will give you also another picture where I have taken this direction to be the z direction and taken this charge q out here at a distance d from the center, put another charge q prime at a distance d prime from the center along the line joining the center and the charge q, or along the z direction. Then Vr, I can write that as 1 over 4 pi epsilon 0 q over mod r minus d at z, that is the potential due to this charge q, and the image charge, which I am going to write in a different color, plus 1 over 4 pi epsilon 0 q prime over r minus d prime z. So, I put it at a different distance, but inside the metallic sphere, so that outside the Poisson equation remains the same. R minus dz is equal to square root of r square plus d square minus 2 r d cos theta. R minus d prime z similarly is square root of r square plus d prime square minus 2 r d prime cosine theta. Theta remains the same because both the charges are on the z axis. So, let us now write the potential V at r to be 1 over 4 pi epsilon 0, that is common, q over square root of r square plus d square minus 2 dr cosine of theta plus q prime over square root of r square plus d prime square minus 2 r d prime cosine of theta. To generate these charges, I am going to do some manipulations here, although they can also be generated by initially looking at two different charges and finding a surface where the potential is 0. But here I am going to just do a little manipulation. I am going to write this as equal to 1 over 4 pi epsilon 0 q. I will take r common, and inside I am left with this 1 plus d over r square minus 2 d over r cosine theta raised to 1/2 plus q prime. I will take d prime common out here. D prime is square root of 1 plus r over d prime square minus 2 r over d prime cosine of theta, close it. What do I want? I want at r modulus equal to r, V be 0. Right? So, let us take modulus r equal to r, or this also implies r equals r. Let us write the potential. So, V at mod r equal to r is equal to 1 over 4 pi epsilon 0 q over r 1 plus d over r square minus 2d over r cos theta raised to 1/2 plus q prime over d prime 1 plus r over d prime square minus 2 r over d prime cos theta. And I want this whole thing to be 0. I can ensure that if I take q over r to be equal to q prime over d prime with a minus sign in front, and d over r to be equal to r over d prime. I have got two unknowns, q prime and d prime, and I have got two equations. So, this gives me d prime equals r square over d, which is certainly less than r because d is greater than r, and q prime equals minus q r over d. So, what I have found is that if I have this sphere which is grounded and I put a charge at a distance d from its center, then if I put another charge here, q prime, this is q prime equals minus q r over d, the radius is r, at a distance d prime, which is r square over d, then V is 0 on the surface, and V is 0 at r equal to infinity. So, we have found this combination of charges that satisfies the boundary condition, and in this region outside the sphere del square V is also equal to minus q over epsilon 0 delta r minus this d vector. If it is on the z axis, it will become dz. So we have found a combination of charges that satisfies the equation, Poisson equation in the outer region, also satisfies all the boundary conditions. We have found the solution. That means potential in this case V r is going to be V due to this q plus V q prime. So what I have tried to convey to you is that using the uniqueness of the solution, we can calculate in certain situations. For example, we have done two examples where charge in front of a plane grounded surface and charge in front of a grounded sphere or grounded metallic sphere, that we can find charge combinations that satisfy the boundary condition and the correct Poisson equation, and therefore that gives me the correct solution for that situation. I'll leave the problems that I did in the case of planar surface, charge in front of a planar surface, for you to try. I'll also give it in the assignment. Thank you. Used